Hello everyone, welcome back to another video for the series. I'm Q, and today I brought a very fun and interesting problem from the IMO. And this problem is, I think many of you who are watching this video might already know this problem because it's actually a really famous one, and it's famous because not because of its ingenuity in solution or like its unique method, but because of its difficulty. So this problem was actually known to be a really is actually known to be a really easy problem that came out on the IMO, and that's why I tried it myself. And surprisingly, my solution aligned with the official solution. So I'm just gonna merge those two and share it. Okay, so find all functions f such that for all reals x and y, the following equality holds. Yes, so for this one, let's do our typical move, very typical move. So our typical move would be substituting x equals 0. That's what we always do, right? Then we get f of 0 equals f of 0 times this. So this is true for all real numbers, all real y. And this implies, obviously, two things. That f of 0 equals 0 or equals 1 for all y in real, like this. Now, let's do our second thing. We have y equals 0, so we have f of 0 equals f of x. Now, this also implies two things. So, first one is when f of 0 equals 0. So, this equation is true when f of 0 equals 0, but what if it's not equal to 0? Notice that f of 0 cannot be in between this interval, because then our right hand side would be 0 while our left hand side is not. Oh, sorry, like this. So, this case doesn't work. Then we know that we have other cases. So that's when f of 0 is not in the interval 1, 2, in the open interval 1, 2. If it's not, then we could obviously divide it and find out that f of x is a constant. And that's because we know that there exist many values of f of 0, but for each case, f of 0 is fixed, so we get f of x as a constant. Notice that we have when f of 0 equals 0, so we could actually divide our cases. So the first one would be when f of 0 is not equal to 0. So if f of 0 is not equal to 0, then we will have f of, I'll just say x because it's the same variable. I mean, it's not the same variable, but here we don't really plus 1 for all, like this. We also know that f of x is a constant. So let's say it's equal to c. Then we know that because both of these are true, we know that this is true. Now let's double check if this is true by substituting our c here. So notice that this is true, and it's either c equals 0 or c lies on this interval, but we know that c is not equal to 0 because f of 0 is not equal to 0. So this is our first solution. So this works. Now, this is a solution that we get when f of 0 is not equal to 0. Now, let's see if we get a different solution when f of 0 is actually equal to 0. So if f of 0 equals 0, we can't really use our same method right here because we'll get 0 equals 0, and that's not really helpful. The same method here is substituting 0 here, and you get 0 equals 0, so it doesn't work. Then we could actually do another typical move, is setting a new variable. So we're going to claim that, let's claim it. We're going to claim that there exists alpha, there exists alpha in 0, 1, such that f of alpha is not equal to 0. So let's say that this exists. And the reason why we give a new variable alpha is because usually when we try substitutions, and if we get no more new information from substituting new values, we usually do this. And the reason why we use 1 here is because notice that if we substitute 1 right here to f of, if we substitute when x equals 1, then we get f of y equals f of x. We get this is true for, it's 1. We know that this is true for all y in real numbers. And because this is true, we could safely assume that, no, let's not assume it first. When we substitute 1, we get actually, before doing this, let's substitute alpha. Let's substitute alpha when x equals alpha. If we substitute this, we get f of, because of the reason why it's open interval 0, 1 is because then if we substitute x equals alpha, this whole thing becomes 0. So f of 0 equals f of alpha times, so this is true for all real y. Now this is equal to 0 and this is not equal to 0, meaning for all y in real numbers. So we know that this is true. Then we know that f of y must lie in this interval for all y in real numbers. Now, why don't we try substituting 1, x equals 1. That way we can get more information. So we have f of y equals f of 1 times for all y in real numbers. So both of these are true. Now notice that this is equal to 0 for all y in real numbers. So notice that this one is true, this one is true, and using those two truth statements, we get f of y equals 0 for all y in real numbers. But this actually contradicts with our claim that there exists an alpha such that f of alpha is not equal to 0. So contradiction. And we're actually, this movement is actually illegal because notice that this is always true, this is always true. Using two true statements, we get another true statement. Okay, so this was our subcase, but notice that it didn't work. So our subcase didn't work. Then why don't we try its converse? Because its converse, so we examined the case when f of 0 not equal to 0, and we found a solution for this section. And well, this whole thing is f of x, and we're looking at this, but we know that half of it, so our first subcase, this doesn't work. So we are going to look at its converse. And if you find a solution from here, then we are going to find every solution in f of x, for f of x. So that's why we're going to take a look at its converse. So our claim would be there exists alpha. Now this time this claim is true because we know that f of 0 equals 0. Such that actually it's converse, so we need to do for all because not like a true converse, but we at least cover. Wait, no, this is a converse because there exists. That means there doesn't exist an alpha such that this is true. That means its converse would be for all there exists such that this equals 0. Yeah, so this is indeed the converse. Now let's continue. Notice that we cannot take the same approach as we did in our first claim because here we will get f of alpha equals 0, so 0 equals 0, and we don't get any new information. So why don't we rewrite alpha? So let's say that alpha is equal to a over n, or a over so alpha is always positive, so a over a plus 1. I think we can do this. Yeah, I think so. For some, no, actually, let's just write it as n to reduce confusion. For some and n in natural numbers. And this is totally fine because even though a is we don't know if a is a rational number or not, but it's still fine to write it like this because a is defined in all real numbers. So it could be irrational too. Okay, now here, oh, this statement is strange. For all, yeah. So what we're going to do here is notice that we have, I'll just write it again here. like this. Multiply n, we get alpha and n. We have something times something, so maybe this would be helpful. So we get f of a equals f of alpha times n equals f of times alpha, and by our equation right here we have this equals f of n times this is true. Notice that for all this equals 0, meaning f of a equals 0. Yeah, but let's take a look at what a actually is defined as here. So a is, we said alpha equals a over n for some a in real numbers, but I want to say that for all real numbers. So in this case, it's for some real numbers, but in this case, a is defined in all real numbers. And that's because, say we have some constant k in this interval right here, and we're going to scale it, like say n. Then obviously this is in this interval for n greater than 0, or negative n, and this tells us that k of n is always in this interval. No, actually we cannot do this. No, it is true, it is true. Yeah. And let's say that n is exponentially growing, so it's really huge. It's a really large number. So let's say that n is a infinitely large number, then k of n is actually defined in all real numbers. Okay, so what I mean by this is alpha is in this interval right now, but as n changes for some natural number n, we could actually define infinitely many number of alphas, and all real numbers could be written as the product of a natural number and an alpha in this interval. Yeah. And the reason why we can do that is because we can always divide a natural number. We can always divide a number. So say that if it's a prime, then we can divide it by itself. So for example, let's say I don't know, like a equals 2.05, like a random number like this, and then we can just define n as 10. Then we get a in this number. So we could actually, by doing this, we could actually find out that all of the real numbers could be written in this form, even the irrational numbers, because just divided by the power of 10. So we know that this is true for all a in real numbers. So f of 0, f of a equal f of x equals 0, and that's the only solution from here. Let's see if that works. 0 equals 0 times 0, so it works. So therefore, our solution to this problem would be f of x equals c for c in this interval. And I think or is a better word. So this actually completes our solution. And yes, the basic structure of this problem, I think it's really fun. Like it used really fundamental ideas, like substituting x equals 0, y equals 0, and we could divide cases, because we know that we have f of 0 equals 0 here. So doing that, I think it's quite obvious to go from here to here. It's quite natural to go from here to here. And we can find our solution here. And for this one, we did another very, I would say, fundamental move by setting a new variable alpha. And that actually led to our solution. So yes, I really enjoyed trying and solving this problem because it's like few IMO problems. It's one of the few IMO problems that I was actually able to solve and get the correct answer with with the complete solution. So I was really excited for this problem and really enjoyed it too. I hope everyone who watched this video enjoyed this solution too. And thank you so much for watching this video, and tomorrow I'll come back with another very fun and interesting problem. Thank you and see you tomorrow. Bye.